This experiment also you have to write the lab report. Maybe next week experiment I will consider just to take the data sheet. Okay. Right. So let's take a look. The background information. What we try to do in this lab we already discussed. Correct. Yeah, only 10 labs is considered for grading. So you can skip either one, or if you submit all 11, I will drop the lowest grade. Okay. Which means technically, if you've done all 10 labs so far, including this one, and then submitting this lab report next week, next Wednesday lab is actually not required technically. Okay. Yeah, that's correct. So if all are good with the 10 labs, we can actually skip that lab and then maybe do a review session. Let's take a look next Monday. All right. So anybody have any other question? All right. Now the idea of this lab, last time when we talk about the early quantum theory, we discussed the gas discharge tube. That is actually beginning of the very early time of 1900. This observation were done. So what they actually done, they had a vacuum tube, and then inside the vacuum tube, they fill the gas, like hydrogen, for example. You fill the hydrogen gas, and then you apply a really high voltage into this, put the two electrodes there, and then apply really high voltage into these two electrodes. By applying really high voltage, actually you can ionize this gas. Okay, so when they observe this one, by applying that and then observe this behavior, then what they have seen, the particular colors comes out. So that's the first observation which led to the idea of the Bohr model after some time, right? So when they do that for hydrogen, they observe like 3 different colors comes out, and they change the gas into like helium. Then they have seen like different colors comes out, and then they try with this, I think, mercury. Mercury is Hg, right? Mercury, and then couple of different other gases they tested. So each time when they have a different different element, what they have seen, the light comes out is actually very unique. They don't at that time there wasn't any other way to detect UV light or anything coming out. They could detect only the visible light. Okay, colors comes out. Now that led to the idea of that this color comes out because of that. At the time, they have idea about how the atomic structure look like. Maybe the atoms idea they had some way. And then the idea is that usually when you have the gas system and the gas, all the atoms try to stay in the ground state, right? That's what they thought. And then if you apply a high voltage, so the gas atom you can ionize. So you put some energy in. As a result of you put the energy in, this gas atom or the molecule can go actually the higher energy state. Let's say this is most ground state n equal 1. Let's say this is n equal 2. And if you do that, then that gas atom or molecule doesn't stay there forever. After some time, it actually go back to the ground state. When it is going back to the ground state, this actually going to emit a certain color. That color is the one we actually observe, and that is a confirmation, the good observation to confirm the quantization of energy. So which means since we don't see all the colors comes out, only particular color comes out, which means this delta E, energy gap between these two state, is actually quantized into HF. Depending on which frequency, H is the Planck constant, right? So depending on what frequency comes out, we can see actually different colors. So that's the idea. So the problem with that, there were a couple of issues with that observation, because they can't confirm anything about the atomic structure or anything. They thought that the whole atom is actually doing this excitation and then so on. But when it comes to the Bohr model, Bohr was able to explain that very properly. So what his idea is that this observation is correct, but what he added up is actually his atomic model. He thought that now, for example, he produced this one for only hydrogen. So the idea was that the Johannes Balmer tested this series, what we call the Balmer series, 1 over lambda, which is equal Rydberg constant parentheses 1 over m square minus 1 over n square. You can say m is actually the final state, n is actually the initial state. Now this is where the atom is initially in higher state, initial state, and then when it is de-excited, this will be the final state, right? So when the de-excitation happens, you will see that energy comes out. So they tested this formula and then figure out this constant. It worked very well. Not for all the type of element. It works very well for the hydrogen, but when the hydrogen and the helium also, it worked fairly well. When the atomic number is lower, which means the lighter elements, this work very well. But if we have the heavier element, for example, mercury, which is very heavy, this formula doesn't work at all. So that's why the Bohr model itself is actually precisely matched with only hydrogen or lighter element. If you have a heavier element, Bohr model is actually not precisely matched. Okay. So that's what we actually trying to investigate today. By using the simple setup, we try to investigate whether this formula is precisely valid for the hydrogen spectrum or not. Okay, that's the plan. We're gonna observe the hydrogen spectrum by using the simulator. Actually, we can do this in class too. We have this gas discharge light. So all we need is actually gas discharge light, high voltage supply, and the diffraction rating. That's all really. We can set up a simple experiment. Then we can observe the hydrogen spectrum from that. And then by observing that, we can actually validate this one too. But the simulator is actually much easier. Now, to validate that, what we have to do, the lambda comes out, we can measure directly from the simulator. Lambda we can observe directly, and the excited state also simulator will show you what is the m, what is the n. Those states simulator will show you. Those we have to record. By recording that, we can actually calculate Rydberg constant. Rydberg constant is actually known value. It validated over several centuries, several decades now, right? So the Rydberg constant, we expecting the value of 1.097 times 10 to the power negative 7, 1 over meter. See what happened to that. Oh, my page disappeared. Let me take a look why. Take a look, something happened. The whole page was disappeared. Okay, very bad. That's okay. It's just writing part. Nothing much to worry. Okay, there you go. All right. So this RH, what we expecting 1.097 times 10 to the negative 7, 1 over meter, right? Because RH is actually should match with this one, right? 1 over lambda. N and M doesn't have. You need those high states, right? So when Bohr explaining this one, he actually explained it nicely because his model is that hydrogen atom has only one proton and the electron is orbiting around it. But electron can actually don't need to necessarily stay on this n equal 1 state. It can have actually many other states beyond that, right? N equal 2, 3, 4, 5, anything, right? So which means if you add a certain amount of energy, this will excite into a next state. After some time, it will de-excite naturally. When it is de-exciting, it will emit some amount of energy. That amount of energy we can detect. Okay, that is the HF. By detecting that color, identifying that amount of energy emitted out, then we can actually validate the Rydberg formula. That's the plan. To do that, by observing the N1 and N2 and the lambda, we can actually calculate RH. Okay. Then if we get in the right number, what we expected, 1.0797 times 10 to the negative 7, we can validate it. Not only that, this RH is actually equal to E0 divided by H of C for the hydrogen atom. Okay, this is valid only hydrogen atom precisely. If that is the case, by using that equation, I can calculate Planck constant. Planck constant is equal E0 divided by RH Rydberg constant times the C. E0 for the hydrogen atom, we calculated last time 13.6 electron volt. Electron volt, if I want to convert into the joule, I can just multiply by the electron charge. Then I can convert into the proper SI units, that is joule, right? So, which means I know E0, and then C is just 2.99 times 10 to the 8 meter per second. By using these two and the calculated RH, we can actually estimate H. So we know what the H should be. That is 6.626 times 10 to the negative 34. That is the basic quantum constant. That is the Planck constant, right? Which means if we get in the right number there, then we can validate this whole model and the hydrogen spectrum in two ways. One is calculating RH, and again by estimating the H, Planck constant. Okay, that way we're not just validating the hydrogen spectrum. By just doing this kind of experiment, we can actually validate the very basic fundamental idea about the quantization of energy. So that's what actually we validating. So that way we actually validating the some way, in a way, quantum physics really. Okay, that's the plan. Any question? Okay, then let's continue. This is fairly short lab, and not only just calculate, we can actually calculate this, right, directly. Let me write that too. Now, since I know lambda, m and n, we can calculate RH. RH going to be equal 1 over lambda times 1 over m square minus 1 over n square. We can calculate those numbers, and also if you take a look, the formula equation is actually look like this: 1 over lambda RH times 1 over 1 over m square minus 1 over n square parentheses. So which means, since I know lambda, m and n, I can actually make a graph, right? Because to make a graph, at least you need 3 or more data points, right? If I have 3, that should be good enough. Hydrogen spectrum actually can produce 4 different colors. So we can make a graph by using 4 data points. If I put this into y-axis, this into x-axis, I should be able to get y equal ax type graph. Okay, this a slope of the graph should be the RH. So which means I can find the RH by using slope of the graph. Okay, that's the other plan. So we can make a graph. X-axis should be. Give me a minute. Okay, so the x-axis should be different between 1 over m square minus 1 over n square, and the y-axis should be 1 over lambda. Then I should get a small graph. By using the graph, I can actually take in the slope. We can again calculate the same parameters again. Okay, that is the first part. And the second part of the experiment, we can actually have different gas tubes. In our labs, we have actually many. We will test at least for at least one or two or other different gas tubes, gas discharge tube. We'll observe the colors, but we may not be able to calculate a Rydberg constant precisely. The reason is this formula doesn't valid as it is for the when the atom is heavier. If atom is lighter, it actually match fairly good, but atom is heavier, it doesn't match. We'll check it out. We'll observe the lambda, we'll observe the M and then we'll check it out by calculating RH, whether we're getting fairly reasonable value for RH for the heavier element or not. But we cannot really validate by using the heavier element. Okay. So that's the plan. So it's fairly very simple experiment, but calculation we have to do very carefully because it's very, very small numbers we are working with, 10 to the power negative 30s and then so on. If any mistakes happen, then the error going to be much larger. So that's the only part. Otherwise, it's very straightforward and easy. Any question? Okay, then let's continue. You can click on the simulator link that will open up in the new window. Seems to be slow a little bit, that web page, but it should open up. I checked today, it was working fine. Give it few seconds, it should automatically load. Okay, good. So it should be, after it fully loaded, that page should be look like this. This is the gas tube what we are talking about. You can see that's a cylindrical tube. These tubes if you buy it from the market, it's not exactly look like this. It's very small, okay, extremely small cylindrical tube, which has gas inside and the two electrode. What we do, we can buy a gas tube separately, and then we have a high voltage supply separately. So the gas tube itself not expensive, but the high voltage supply is expensive. So that's fairly simple setup. Even we do it in class setting, but the observing these colors is little tough. We have to have a very good dark room, so have to darken out whole lab and then so on, because observation are little tough to do. All right, now when you first observe this simulator, you will see the gas tube and one atom right here. And I can pick the different atoms. If you go into your right hand side, you see right now it's selected hydrogen, right? But I can select mercury, sodium, neon, and then I can configure even the atom, whatever the atom I would like to do, right? And let's start with the hydrogen, because we're interested to see that number, especially for the Planck constant, right? Because if we're getting that right number there, that's a good, very good confirmation. All these theories, what we actually going to discuss next week. Okay. All right. So now we have the atom right here, and then to excite that, we can actually bombard that with the electron. That one way actually we can excite. That will actually generate the colors, and that's how this simulator set up. Now to do that, you have to actually produce the electron from this electrode. You can see on the top right here, battery is set up to the electrode, okay? And this is not really high voltage. You can see it's fairly low voltage number, but in reality, you can't really get this done with this amount of voltage. We need really high voltage. Okay? You can click that and then drag all the way to the positive 30. Doesn't matter, positive or negative, it just changes the direction of the electron flow. Otherwise, it doesn't matter. And the inside here, it's okay to have one atom. That's fine, I think. And here you can click continuous. Now, as soon as you click the continuous, you can see electron comes in from the electrode, it hit the atom, and then as a result of that, you can see certain amount of energy disappear, right? So that disappearance energy you can see going out as a photon. Photon has a different colors, right? Photon is actually our color, the energy packet, what we generally call. So now to identify that, you have to go into right-hand side. You can see spectrometer term. Just click on that. Then you will see the spectrometer. Then if you wait and see, then that spectrometer will show you the wavelength values of that the photon coming out due to that collision, right? You can see UV range right here. That's fairly high energy coming out, which we cannot detect. Because of that, we're not going to do any calculation with that part. We can't do those energies by with our naked eye, right? But all the other colors you can observe, right? So if you look at it here, you can see 4 different colors: violet or the purple color, and the blue color, and the light blue color, and the red color. Okay. So now all I need is actually this color wavelength you can actually get from here. If you go into this scale right here, it has a nanometer scale. Wavelength is a nanometer. We know the higher the energy, it should be the lower the wavelength, right? So towards the 400 violet, and then close to the 500 blue, and then close to 400, or the close to the 500 is the light blue, and then close to about 650 red. Okay, so those numbers we can get. Now what we need to do, in terms of data, we have to extract that wavelength for 4 different colors, and also we have to get which states are actually responsible to produce these colors, which is the initial excited state, which is the final state. If you go into the right hand side, you see atom is excited and the de-excited, right? You see that? So when it does, you can see different color waves appear. Now I have to exactly detect these numbers, which state number is the initial state, which is the final state when the de-excitation happen. Now to do that, it's very difficult to observe this way because it's moving very faster. If you click on run in slow motion mode, now you can see when the atom de-excitation happen, I can pinpoint which is the initial state, which is the final state. Those two are the numbers we need. That is the M and N, and then this is the lambda. As far as I have all those information, only those are the information we need. Lambda, M and N. As far as we have those, we can just simply check this out, whether I'm getting the Rydberg constant correctly. If I get it, then I can further test it out whether I can get the Planck constant correctly. Okay. So that's the plan. So it's very simple calculation, but getting that state is actually the key. If you don't have that correctly, the error going to be very, very high. Okay, and when you observe in the states, you can see right here when you go to the about tree, you can't see the numbers, but you can see the lines, right? This is second one, third one, fourth one, fifth one, and sixth one are very closer. So I have to pinpoint where's the initial starting point of the atom. Okay. Question. This icon you can just leave it 20%. That's fine. If you increase it, you can see more and more electron comes in. It's not really anything important. So we can leave it maybe like 20%. That's fine, because we don't need actually more there. What we need is actually at a time to observe exactly when that de-excitation happens. Okay? So the best way is that you can reset this part, this spectrum part. There's a reset button right here. Then all the colors disappear. Then let it start again. And if you let it, okay, let it move. Now you can wait until the one color appear. Then you can see second to one excitation is actually not producing there. So the third to 2 producing actually red color. So that's the difficult part. Okay, now you can see it's rapidly moving, it continuously moving, but you have to detect which color is actually emitting, what is the initial excited state, what is the final state. It's not always jumping from 2 to 1. When it's jumping from 2 to 1, you're not going to see any color, it is UV. So to produce the red, it should jump from 3 to 2. That exact moment, exact behavior, you have to observe and then record. Okay, so that gonna take a little bit of time, because if you're not sure which is the excited state first and the last, you can let it go and then keep observing. That's all. It's not big deal. It's gonna continuously produce the same color again and again. Okay. Now let's let it run. 2 to 1, nothing. When it go into a 3 to 1, also nothing. It's UV range. When you go to 4 to 1, nothing. 2 to 1, nothing. It's on the UV range. That's why we don't see it. Now you can see it went to 6 and then come back to about like 3 and then come back to 3 to 2. When it coming from 3 to 2, you saw that red color line right here, right? Wave, red color wave. So that confirm when it jumping from 3 to 2, it is actually producing the red color. If we're doing this in class, we actually going to do oppositely, because we can't really see this behavior, which is the excited state, and then so on. If we're doing this in class, we detect the color and then we actually re-investigating what are the possible excited states are. But in this simulator, we can actually do we can observe this excited state. Because of that, we can easily validate the Rydberg constant. Okay, that's the plan. You can see whenever it emits the red color, a small dot will appear on the spectrum. Good. Any question? That's only a difficult part. The rest of the calculation and everything is actually very easy. Okay, let's let it run. When it goes to the higher state, like now it is on 6, right? So then you can maybe try to go slow-mo, but the fast forward this one, or let it run in slow-mo mode and then see what is the next excited state. 2 to 1, we don't see it, UV region. When it goes to the higher state, you can stop and then make sure that excited state, now that is on number 6. Let me check, that is on number 5 now. Okay, it's not 6, it's on number 5. And let's see where it's going now. Jump into 4, jump into 1, there's no color produced. Now you can see it went to 5, actually went to 4 and then jump into 2, then that is actually making light blue color. So you can see this dot appear there, right? So that the information we need. We need to have exact color, exact starting point, exact ending point. Now, if you stop right there, then you can see this wave thing right here. So that wave confirm where's the starting point and where's the ending point. Everybody got that idea how to get that point, because if you don't get that point correctly, then whole calculation will be incorrect. Okay. So you have to make sure the starting point of that wave and the ending point of that wave. Question. You see that? Anybody have any question? Show you that again. Hiding. I have to reset that anyway. Okay, let's reset that. Okay, that's my spectrum is hiding, and then the spectrum energy states are hiding because I try to zoom in too much. Probably that's okay. So let's reset this one and then see whether I can do that properly. Okay, so that's fine. Let's reset this one. You have to make sure that starting state and the final state, because those numbers are wrong, your calculation will be very bad. Okay? Otherwise, that's it. Then you repeat, let it run, and then observe that. That's all. Let it run this again, starting with the slow-mo mode, spectrometer, and then let's do continuous. Keep the mouse cursor here on the pause button. Whenever you see a color comes out, go into the higher state, then you can stop and then see what's the next state is. There, starting from the 6, that's what I want to show you earlier. You need to make sure that is starting point, okay? So because separating state 5 and 6 is difficult. Now it is on 6. If it is on 5, you see this small circle is actually crossed from this top line. So that's the one I want to show you earlier. Now it is good, I think. All right, then let it go high energy. Still high energy, no meaning. 2 to 1. Let's see, it should, if it go 3 to 2, then that will produce a color. Okay, starting at 3. Yeah, so you see that? That's the red color. Now that's the data actually we needed. Okay, now let's record that. Question. Any question? Okay, then let's record it. So the radiation emitted, you have to record it. This is on visible range. We are observing the red color. And the wavelength of the red color, I have to measure from here. That also there are going to be a little bit of error, but that's okay. You can see this nanometer go from 600 to 700. The minimum measurement I can do each 10 nanometer. This is 610, 20, 30, 40, 50, 60, 70, 80, 90, 100. Yeah. So each 10 nanometer we can do, least count is 10. So half the least count is about like 50 nanometers. Error going to be very high, but that's okay. I think that will produce a little bit of error. So this is now at 10, 1, 2, 3, 4, 5, very close to 6. I'm going to read into 660. Okay. So it's going to be 660 nanometers. Now you can see if your data table showing you 3 decimal places, that is not good because I don't have that much accuracy. I can only read down to, there's no decimal places I can read at all, right? So let's get rid of all the decimal places. Format cells, right click. So the decimal places put in there is actually not meaningful. I can't read any decimal places at all. In terms of unit, I'm going to keep the 10 to the power minus 9 on the top because it will be common for all of this. When I do the calculation, I don't need to write that 10 to the negative power again and again. Okay, I'm going to keep it on the top. That's going to be same for all of this. Now, excited state is starting at 3. M is 3, and then excited state going back. It doesn't go all the way to the 1. It actually go to the second excited state 3. Okay, 3 to 2. Those two also, you can't have any decimal places. You have to reformat, format cells. Make sure there's no decimal places at all. It's just a number. I can't really do any estimation or anything other than just a full number there. Question. All right. One other thing we can do here, very little bit for further calculation. When you do it, will be a little bit easier. If you go back to the Rydberg constant value, that actually 1.097 times 10 to the negative 7, right? So which means that 10 to the negative 7 come from the wavelength. So I can, instead of reporting this with the 10 to the negative 9, if I record this with the 10 to the negative 7, and then this number should be 6.60, right? So if I record that way, it is easy when I do the table number 2 calculation, right? So it not required, but if I do that way, this 10 to the negative 7, I can keep it without putting into the calculator, okay? Because of that, I'm gonna reformat this wavelength into now 2 decimal places, because I'm recording now up to 10 to the negative 7, not to 9, okay? You have to be careful how you record the data. If you're recording it to the 10 to the negative 9 with the nanometers, you should not have any decimal places. But if you record to the 10 to the negative 7, you can have 2 decimal places. Okay. Question. Let's do one calculation to see whether we are getting the right number. Okay, let's do 1 over m square minus 1 over n square. This is going to be parentheses 1 over m power 2 . Let me write m is actually the final, n is the starting. So I did a mistake here. Highest excited state is actually the n, and then where it is actually going to the de-excited state is actually the n. Okay. Please change that 2 letters here, because it always not going to the ground state. That's why I did not wrote here is it has a ground state. Where it is starting will be the excited state. Where it is actually ending is the de-excited state. Okay, that's the final. So in this case, final is 2, starting at 3. Okay, now it's good. I changed these 2. Let's do the calculation. Equal sign, parentheses 1 over m square, that is 2 to the power 2, close brackets, minus 1 over, that is 3 to the power 2. If you miss that, actually you will get a negative sign. Doesn't matter how you do this. 1 over m square minus 1 over square doesn't matter technically. But if you don't identify what is the excited and the de-excited state, you will get extra negative sign here. Okay? If you get that, all you have to do ABS, absolute value. That will correct that out. Let's do 1 over lambda also here. Unit going to be 1 over meters times 10 to the power positive 7, because it's 1 over lambda, equal sign 1 divided by this guy. Okay, now let's take a look the Rydberg constant, at least 1, before we proceed to the data. This should be meter per second, right? Equal sign, RH should be equal 1 over lambda times 1 over m square minus 1 over n square, right? Let's do that calculation to see. So RH from this equation, if you're calculating this whole part is RH going to be 1 over lambda times 1 over this whole part, okay? So I can do it easily. Equal sign 1 over lambda we already calculated. And multiply by 1 over this whole part. Do parentheses here. Okay, 1.91. So in terms of number, what we expecting, we are fine. Okay. So I had, I think, mistake here. This should be 10 to the positive 7, because it 1 over lambda here. Okay, question. All right, so that's why I keep this number right here without putting into the calculator. Okay, if you don't see it, why I keep this 10 to the positive 7 here, because I don't need to worry about when I do the calculation. I just need these two numbers. Okay, so I'm going to keep that 10 to the power value here without putting into the calculator. So when I do the calculation, then it is a little bit easier. Okay, that's why. Okay, any question? All right, so I think in terms of expected value, we are fine. There's an error. We are expecting 1.097, but we're getting 1.091. That reasonably enough. And also these two numbers, I think we can do three significant figures. Technically, we should go one significant figure because these are states. States doesn't have any significant figures. Because of that, whatever the number we can physically measure with the physical units is the wavelength. We'll actually use that amount of significant figure for these two, because if I round this into one sig fix, that's going to be a lot of error when we compare to the given Rydberg constant value. Okay? Because of that, we'll use 3 sig fig on these two. So it's work fine for the red. So all we have to do now, this is enough to understand the Planck constant and everything. But in terms of validating this graphically, we need actually at least 3 more data points, at least 2 more data points. More data points you have in your graph is more accurate. So what we're going to do, we can let the color production right here to continue and then see what other colors I can observe. Right now I observed only red color when the transition happened from 3 to 2. Okay, let it continuous, and then we'll observe the other possible colors. Whenever the other possible colors appear, we'll record the states and the wavelength from our spectrum here. Okay, you can see spectrum has a least count about error is about 50 nanometers. It's not 50 actually, 5 nanometers. It actually not really big deal, because this number we calculated fairly reasonably accurate error is on third decimal place. So in terms of accuracy, it's good. So that error, 5 nanometer error is actually not big deal at all. When I read earlier, I read this number into 660, it may not be 660. It should be maybe in between 650 and 660 nanometers. It may be 655. So depending on there, you're going to get that third decimal place error. Okay. All right. Question. That's all. Then we'll continue. So let's take a look what other colors we can observe in here. Let it run this one. Whenever you see the excitation into a different state, it's better to stop and then look at that state first. Okay. Now you can see it is on 5th level. You can see that is on not the 5th level, actually that is on 4th level. That's the difficult part to identify. That is the one I want to actually show you earlier couple of times, because when that excitation happened to the 4th, 5th and 6th, you have to be careful, because it's difficult to see what is the exact starting point is. If you don't have that, that's going to create a lot of it. Now if you take a look carefully, now that is on 4th level, right? See, bottom of that small circle is actually touching the 4th line right here. It is on 4th state. So that's the point you have to be careful. Otherwise, rest is very simple. That is on 4th. Let's see where it be exciting. Goes to 4 to 3. Doesn't produce any colors. 2 to 1 is UV. 6. Now it is on 6. 5. 4. Okay, so now I have a different color. So the purple color, I'm not interested red color any longer. Okay, if that appears, you can just continue until you see a different color. Okay, so we interested only different type of colors. So let's take a look, starting point of this one. So that's the important part. I think it started at 6, maybe 5 to 2. So let's try with 5 to 2. We can do a little bit of trial and error there if needed. So because you know what we're expecting in terms of Rydberg constant. If I see large error there, I can go back and reinvestigate that. Not big of a deal. So let's do 5 to 2. 5 to 2. And then pink color is, purple color is right here. So that is on 400, very close to 410. So I'm going to read into 410 nanometers. Okay. So there are going to be little bit of error there, 4.10 into 10 to the negative 7. This is purple. For violet, you can say these two actually you can click and drag because we already use the cell values. And this also for the next one you can click and drag. Okay, 1.161. I'm expecting 1.097. So that's fine. I think it's still not bad. And the one more thing probably we should do, we should actually record these EM radiation colors also with this one. Right here in the table, I forgot to put that column there. Maybe we should include that too, but that's can be done easily if I shift this whole table one cell thisward direction. I can add this column right here. Only for formatting purposes, that column remaining there may be actually good. This you have to redo the calculation again. That's going to be 1 over lambda multiplied by 1 over this value. Okay, so then you can click and drag. Okay, so a little bit of higher error there. The second one, that's okay. Just we'll leave it. Question. Okay, let's do the percentage error also for the Rydberg constant to keep track how much error is happening with our readings. Or let me copy paste those right here. This is the command which I'm using for, it's going to be parentheses 1 over m square minus parentheses 1 over n square. And this one for 1 over lambda. 1 over lambda, and then this one is actually for the Rydberg calculation. I'm reading the cell values from the table 1. Okay. All right, any question? It's fairly simple calculation, nothing much to do actually in terms of calculation and everything. And let's compare now, since I separate out that 10 to the power value, when I do the percentage error also, I don't need to worry about that. I can just compare expected value and just this number, okay? Which means ABS parentheses expected 1.097 minus calculated value on C number 18 divide by expected 1.097 multiplied by 100. So it's very low percentage error there, but the next one may be a little bit higher. So this one have about 5% error. Maybe either we reading, either we have a fairly large error with our lambda, or we reading that state, initially excited state starting point, maybe we reading it wrong. So we can check that whether it is 6th state. Yes, I think so. You can see if I start with the sixth state, I'm getting really good number there. So which means we should not really do the data changes to see that, okay, that is not a good way. But what you have to do, go into this one and then try to observe it as accurate as possible. Okay? I did not see that starting point as a sixth state. I saw it as a fifth state. You need to take a look whether this wiggly, this wave, the purple wave is actually all the way going to the sixth line. That's a very difficult to see there because 6 and 5 are very close to each other. That's why before this gray circle, the atom jump back into the next be excited state, we have to actually physically or manually or physically observe that initial state, okay? So that's the only way we can do this too correctly. If anything there, this error going to be so high. Quick share. Let's check it out. Planck constant too. You know Planck constant expected value should be on Joule second, right? And expected value is 6.626 10 to the negative 34, right? So let's check it out whether we can get that equal sign. Planck constant from our Rydberg constant going to be ground state energy of the hydrogen atom divided by the Rydberg constant multiplied by the speed of the light, right? So let's see that. Ground state energy of the hydrogen atom 13.6, but electron volt, if I want that in the SI unit, I have to multiply that by charge of the electron 1.602 multiplied by 10 to the power negative 19 divide by parentheses Rydberg constant we calculated this number multiplied by 10 to the power positive 7 multiplied by speed of the light 2.99 times 10 to the power positive 8. It's showing you it as a 0. The reason this number going to be very small decimal value, that's what I earlier yesterday also telling you. You may have to make sure it is in the scientific format. Okay, let's reformat this whole thing into scientific format. Format cell scientific, maybe 2 decimal places plus the number. 6.68 times 10 to the negative 4. So we are in the right number. So that confirm our observation is correct. That confirm the quantization of this idea of quantization of energy is valid. And also that confirming the Planck constant is valid. What's the expected value is there. So what's the Planck constant we expecting? That should be 6.626 10 to the negative 34 in terms of SI units, right? So let's compare this. Equal sign. Expected value ABS parentheses 6.626 multiplied by 10 to the power minus 34 minus calculated value is on E now is cell number 18 divide by parentheses 6.626 multiplied by 10 to the power minus 34 times 100. So the percentage error is about 0.8. So our whole calculation is very good. Okay, question. Okay, let's continue now. The one color and the 2 colors we done. This also you can click and drag since we use the cell values. It will do the calculation automatically. So far it's good. Now, if I want to really test this out with the graph, I need actually at least 1 more data point or 2. More data is the better, right? So let's take a look other possible colors in the hydrogen spectrum. Okay. Anybody have any question? all we have to do, let this run and then observe, continuously observe for other colors. Okay, let's do that. So let it run. I will keep the mouse cursor here after I click the play button. Then whenever I see atom goes into a higher state, 2, 3, 4, 5, and then 6, I can immediately pause it and then check it out where's the starting state and check it out the final state if the colors is different, right? Two more different colors should appear here, but you have to give it a time. Okay, it doesn't show up immediately. Let it run for a while, you will see that colors appear. That is, figuring out that initial state is the key, because when it goes to the 4, 5, and 6, it's difficult to see actually whether it's on 4th, 5th, or 6th, because those three lines are very closer. There's no way actually zoom in right here in the simulator. Only way to zoom in is actually on your web browser. So you can zoom in the web browser and then observe a little bit carefully to identify that now it is on 5th. Okay, that's the only way to do, because simulator doesn't have the zoom in there. Okay, let it run. Okay, now there's a different, no, oh yeah, light blue color. Oh yeah, we can actually read that from here, right? So in the middle of the particle, that actually tell you a number, that actually tells you the starting point. Is it the starting point or the final point? You have to be careful. So if it is a starting point, then we find. If it says the final excited state, that's not good. Okay, I think it changes. Okay, wherever the particle is, it show you the number. You can read from there actually. That also fine. Then you have to observe the both places here in this state diagram right here and the middle here. That's a good idea. Yeah, yeah, you can do that. So this case, it started at 4 and then go to 2, right? Then I have a different color, that is, we can say light blue, right? So what's the wavelength? I have to read from here, that is 400, 10, about like 15 nanometers lower than 500. We can read into 485 maybe. That's the closest we can do, right? 4.85. There will be a little bit of error there. Try to read it as accurate as possible, but we can't read anything beyond the 5 nanometer level, right? Because that's the error we can estimate there. Least count is just 10 nanometer on that scale. Is it 4 to 2? Good. If that is correct, then I should see very nice number for my table number 2. If those two numbers are incorrect, then I see large error here, right? So light blue, that's totally fine. I mean, it's a trial and error method. You can just check it out, what number I'm getting here, how much error is actually happening. So that's good. I think I observe it correctly. So error is less than 1%, and the Planck constant is good, and the error for the Planck constant also very low. So that observation is good. Actually, that's good. Earlier, one of you mentioned that you can detect that by using this, by observing this number. Yeah, because that number changes wherever the atom is statewide. Yeah, you can do that. That's fine. Use any method you like, doesn't matter. Okay, any other question? Okay, then let's continue. 4 to 1, there's no color, right? That goes to the IR region actually. About 3 to 2, red, right? 3 to 1, no color. 6 to 1, no color. There should be one other color we should be able to see. 5 to 1, nothing. 4 to 2, same light blue, we already have it. Dark blue actually appeared there, right? But I did not point that out properly, I think. Okay, let us continue. It will appear again. Dark blue is the other color, okay? Yep, that's the dark blue. But I missed that to read it properly. That's a dark blue. I'm waiting to see the dark blue actually because it came out earlier, but I missed that. You can see now one other thing. This excitation is actually very random, so you can't really force atom to really go into certain excitation. Even how many number of electron come in and then gives the energy, it's happening very randomly. Right? So that's other thing really. Light blue, purple again, purple again. Is that the dark blue? 6 to 3. Yeah, that's the dark blue. All right, so that goes from 5 to 2, right? Okay, so just we can say blue. And the wavelength I can read from here, maybe 410, 20, 30, maybe 435, which means 4.35. And let's try with 5 to 2. That's what I observed. If it is wrong, I can easily see that when I calculate the Rydberg constant, right? So let's check it out. Blue. Check it out, Rydberg constant. I think that's very good. Yeah. So that's the perfect number we're expecting. Error is very low. So the Planck constant also very good. All right. So that's the only colors I think we can see on hydrogen spectrum. You can let it go now, like by taking out the slow-mo mode and then check whether there's any other new colors appears. We need to make sure we record all the colors, possible colors, right? You can even test this with the, instead of single atom, you can actually put the multiple atoms there if you want to. If you click on this other option very top, it says one atom. You can instead click multiple atoms and then put the continuous mode and then click the spectrometer. Then you will see all the colors appear at a single time. But when I reading it one by one, it's not a good idea because I don't know which atom is producing that color. It's difficult to see that. Now, I just need to make sure whether there's any other colors appear or not. Okay, that's what we're observing here. Seems to be we are fine. There's no other colors, right? So that's the idea. So you can have only that particular colors depending on the element in the gas tube. So you can't see every single color comes out. So that was the observation they were doing very early time on the 1900s, which is very curious at that time, and then which led to all sort of those new stuff we discussed with the last class, and then we'll continue the discussion next class. Okay, any other question with this one? Everybody have the calculation done? Table 1 and table 2 by now should be completed. Okay, then let's take a look now. I can do now, since I have at least 4 data points, I can make a graph, right? So let's make a graph. To make the graph we discussed earlier. So what we interested now, making a graph versus 1 over lambda versus this whole part, right? Excited states 1 over m square minus 1 over n square, that whole thing. So we have that data here. We just need to make the graph. Make the graph, and also you need the picture of this one, right? So it's better to take a screenshot. Doesn't matter, you can take the screenshot here with the multiple atoms, or you can take the screenshot with the single atom. Doesn't matter what you take, but you need one screenshot, okay? And then I will add that screenshot also to here to make sure we have everything. But that should go into your procedure section, okay? Any question? Okay, so let's get rid of all of these. We don't need that. We just need only this part. Rest we can keep it visible. So that's our. I'm going to name it this as a figure 1, but that should be on your procedure section, right? Simulator to study gas discharge spectrums. Spectrums, okay. Question. And then let's make a graph. To make the graph, you know the procedure now, usually scatter plot. Okay, I don't usually add the data. I'm going to add the data later. But that's up to you. There's various ways you can do this Excel graphing, okay. Click add data, right-hand side top. Then we'll select the data, and X value should be 1 over m square minus n square. Those are the data on F8 to F11. And then I need 1 over lambda, that is also table number 1, G8 to G11. 1 over lambda. Click OK, click OK again. Now you will see the graph. And double click on the graph. And then we'll add the trend line, axis titles, and the trend line, both of them. You can see the graph is actually towards one of the corner of the graph sheet. That also looks not nice. The reason actually we don't have data points on here, it is starting from the 0. You can get rid of that part. It's okay to even keep it. Doesn't matter, because then we can see whether the graph is really going through 0 point by extrapolating or not. Otherwise, you can start the x-axis somewhere here, maybe like 1.1, 0.11. Then you can get rid of this space, empty space, okay? Let's take a look first the slope of the graph, trend line, double click, and the right-hand side, very top trend line options. And I can click all 3 because this is a graph should be look like y equal mx. And R square value tell you how perfect the graph is. I'm getting exactly 1 for R square. That means the data set is perfect. Of course, that should be because we are using the simulator, right? So there's nothing wrong with the data then. So that's why we get in that perfect answer. And then the Rydberg constant should be the slope. And you can see Rydberg constant is also perfect. I'm getting 1.09 multiplied by 10 to the 7 because that I keep it separately. Okay. That's it actually. Very, very simple experiment. So let's continue here. Add the chart table. That's going to be the difficult part now because I have to do the chart table 1 over m square. I'm going to do double parentheses here. Parentheses 1 over m to the power 2 minus another parentheses 1 over n to the power 2. That is the x-axis, right? Y-axis is 1 lambda. You can insert those by using the insert function. I'm going to just type lambda here. Okay. Right. This is for hydrogen. Leave it like that. X-axis, I can just copy paste right in this part directly. No units. That part should go here. And the y-axis, there's a unit that's going to be 1 over lambda. Lambda, right? LAMBDA, I think. I did a mistake here. It should be lambda. There should be m. 1 over lambda, or you can put the you can insert lambda actually by using insert function. Okay, 1 over meters, close bracket, but I separated out that 10 to the power value, right? You remember that should be there, right? So this should be 10 to the power positive 7 times 1 over meters, because that must be show up because I separated out here. Okay, you don't need to necessarily, you can actually include that here. For all of these numbers, you can do scientific notation. You can see it work nice with when we do the Planck constant. Planck constant function, let me copy paste that too. It's gonna be H function for Planck constant. And also this is for the error for the Planck constant. We done the error for both Rydberg constant and the Planck constant. Let me copy paste those two also. It's going to be PE for RH. And it's going to be PE for Planck constant, okay. All right, so this is PE for Planck constant. All right, any question? Those are all the functions you may need when you do table number 2. Question. Graph is nice. The earlier I mentioned that you can actually extrapolate the graph backward direction. If you want to do that, all you have to do go into the trend line options. It says backward. Then you just need to put the number there and then see how far it extrapolating. See if I put 1, that too much. If I put 0.5, that also too much. Let's try with 0.1. Not enough. 0.12, 13. 1.5, you can see it should pass through 0, 0, right? So that those kind of analysis you can do, but we are not really much interested that. Instead, we would like to see the graph sometime. If we want to do that, you just need to double click on here, x-axis, and then x-axis options. Minimum point of the x-axis you can change. Let's change that into like 0.11. If you do that, you can see the graph extended, right? So sometime, most of the time, we would like to see graph throughout our graph page, not anything else, right? So sometime we would like to extrapolate and then see how the graph is look like if I extrapolate. So in this case, we can actually change the behavior of the graph a little bit. And also y-axis, you can do the same thing, starting point. Axis option, you can do a starting point instead of 0, maybe 0.1, maybe 1.12, maybe 1.4. Yeah, that looks better now. So likewise, those are the simple adjustment. Okay, I think most of you know. So it's not a big deal. This also I can do maybe 0.13. Okay, now it's good. You can see graph. Usually if you make a graph should be nicely cover the whole graph sheet, not the part of the graph sheet, not should be on the one end or the other end or just in the one place. Okay. So sometime that depending on the study, actually, sometime we would actually keep the graph that way because we would like to see where the intercept point, for example, if it is going through the 0, 0 point, for example, those things we would like to see precisely. Then sometime we would keep the graph in one corner. But in this case, we would like to keep it this way. That's better, I think. Let's name the graph here. This is going to be figure 2. This is again, I can just copy paste this directly, right? Whole part, because we just renaming it. Okay. Right. So question. Okay, say hydrogen spectrum. All right. Any question? Okay, then let's continue now. Let's complete this table also, and then we'll take a quick break and then come back and then complete the table 4. And then we're done actually. It's a very simple experiment, nothing much to do with this simulator. So in table 3, anybody have any question so far with any calculation or anything? Okay, so let's take a look the percentage error a little bit. We done again the percentage error earlier, but we did not did the calculation from the graph. So that's what we're going to do here, right? Rydberg constant, I can keep that 10 to the power value is still separated out if I want to. Otherwise, actually, you can include it here too. Meter -1 per meter. And percentage error, there's no unit, but sometimes we just put the percentage sign there. Planck constant, joule second. And the percentage error, just the percentage sign, okay. And the calculated average means since I did the calculation with the constant 4 times, so I can average them out, right? So equal sign, average, AV command, and in average, I want to get all of those 4. In table number 2, C18 to C21, close brackets. But I'm going to include that 10 to the power value there. Multiply 10 to the power 7. Now, if you do that, it will give you an error because it will count it with the average command. I can't do that, okay? So that will be a problem. You can see either it show you like the error sign or maybe like the number sign. So if you see the hashtag number sign, then actually what you have to do, extend the size of the column, you can just click on the very top and then extend that. Or it's better to go here and then reformat this into scientific notation. That may be the best way because it's a large number, right? We don't like to have it that way. Scientific, one number and two decimal places into 366. Okay. So now it shows you nicely Vt to the power e plus 0.7 mean 10 to the power positive 7. So that's the command I used for that one. Is R of H is calculated average. Okay, LAVG. Let's compare this again, the calculated average with the expected value, equal sign, ABS, parentheses, expected value 1.097 times 10 to the power positive 7. You can just type everything right here, 1.097 times 10 to the power positive 7 minus calculated average on C29 divide by 1.097 times 10 to the power 7 times 100. It's about 0.1% error. So that is the PE for Rydberg constant. Okay. All right, any question? Okay, let's do the Rydberg constant from the graph. The slope in front of the graph is actually the Rydberg constant itself, right? So the 1.0963, I can just type here 1.0963 e to the power positive 0.7. This one you can just click and drag, that will do it automatically. So R of H from graph is just equal slope of the graph. Okay. Any question? Okay, then let's take a look at the Planck constant also. So we know how to do that calculation earlier. We done it here. It's the same command. Okay. So the E0 ground state energy of the hydrogen atom divided by Rydberg constant times the speed of the light. Okay. Equal sign, ground state energy 13.6. It's easy to remember in electron volt, but we need SI units here. So you have to multiply that number by 1.602 times 10 to the power negative 19 to get the joule, divide by parentheses Rydberg constant calculated times 2.99 times 10 to the power positive 8 for the light speed. If it shows you 0, which means it's too small number, so I have to just reformat these two cells into scientific format. Scientific, one number, two decimal places, then it will show you the number. Okay. And this one you can click and drag, that will do the calculation automatically. It's the same command which we used earlier, but let me add that also into here. So this will be Planck constant H from RH calculated average. Okay. R cal AVG. And the PE for that equal sign ABS parentheses expected value 6.626, right? Let us check that quickly. 6.626 times 10 to the power. You can, when you're writing 10 to the power value, you can either write that way, like the normal way, 10 to the power value, or you can actually do E plus 34, that will automatically reading as a right value. Okay. So if I want to write that way, large E, negative 34, that will reading as a 10 to the negative 34. Okay, minus sign. Calculated average is on E, cell number 29. Close brackets, divide 6.626 E negative 34 times 100. And then click and drag. Friction, that is PE for the Planck constant. Okay, guys, any question? No problem. Okay, let's take a quick break and then we'll start the next part. That part actually we can't do the detailed analysis like we done earlier. All we're gonna do just to investigate the other type of a spectrum with the heavier elements. Okay, let's try that. Let's take a quick break first. All right, so I think anybody have any questions so far? Okay, so let's check it out this for the other heavy element, because not only hydrogen can actually do this observation we done for the hydrogen gas charge tubes. This can be done with the other type of gases too. Okay, so let's take a look. I included a little bit of information here. For example, you can see the Bohr model information, that something extremely important in terms of final exam, because Bohr model is one of the important thing we discuss on the chapter number 6. Okay, and you should take a look again. There's no proof here, but the basic ideas there, but everything we discussed very in detail last class. All right, so let's take a look the last part for other type of gas discharge spectrums. Now, all we need to do, if I want to select a different element, I have to right-hand side, you can see the selection tool here. I can do at least 3 different type, very easily: mercury, sodium, neon, or I can actually configure anything I would like to study, right? That also possible, how many levels I need. I can define my atoms accordingly, actually, right? So that also possible, but at least let's take a look the other 3. Okay, so mercury, we'll run this in slow-mo mode again. Mercury will not produce, I think, many colors. I think it might, let's see how many colors it producing. Easy way to do it, go to the multi-atom system and then take a look how many colors it actually producing, right? That's the easy way. Let's do that there. Let's reset this one. Let's put the mercury here. Let's check it out how many colors it's making. Purple, blue, green. There's yellow color, red color. Actually, that also producing decent amount of colors, right? So, and also there are a couple of other colors very low side of the UV spectrum. Not many, but few colors are there. We can study all of them actually. Let's do that. Let's go into the one atom system, and then already purple color appear, but I think I missed that. There's the blue color. Okay, so the blue color appear from 5, 6. You have to read the now. You can see these numbers are hiding. So when you're reading, you have to be careful, right? So it goes from actually 5, number 6 level to number 3. So let's go and reformat this now. We are working on heavy element number 1. We'll say this is atomic spectrum for mercury. Because we can actually do more than one color, okay, for mercury. And the color we're doing here, purple. We'll do only visible part, but technically the other also we can observe there in the simulator. But if you're doing this in person, in class setting, the UV region, you can't really see. You can only observe the visible region, right? So the, which color we observing here? Not the purple, right? It's a blue. Blue color. Wavelength, because the same color, but actually wavelength can varies, right? If you remember last experiment, we have seen the huge variation of wavelength on the colors. But in this one, we can't read that much accuracy. This is going to be 400, 10, 20, 30, close to 40. I'm going to read into 440 instead of 435, okay? Which means 440. You can write in scientific notation actually 440 and 10 to the power that negative 9, I can write E minus 0.9 nano. Then if it will show you zeros because I have to format this whole area. Right click, format cells, scientific notation, 3 significant figures, okay? 1 number, 2 decimal places. Then you will see the number. We write earlier by separating out the 10 to the power value. We can still do that, but we don't need to necessarily. Then we can put here meters. Okay. And the states, excited state is starting from 6, go to number 3, right? So it goes from 6 to 3. This should be actually N. This should be in our formula. Excited state 6 and it end up at 3. These sides should not have any decimal places. Right click, format cells, get rid of all the decimal places. That is just a state value. Just we'll take a look, Rydberg constant value, whether we can get that number correctly for the heavy elements too. Just to see, okay, whether we're getting or not. We done the detailed analysis earlier for hydrogen atom. We don't need to repeat everything again, but this will not fit perfectly. There's a modification we have to do, but let's take a look. It's going to be then 1 over 1 divided by parentheses lambda, this number, multiply by another parentheses 1 divided by m to the power 2. M is E38 power 2 close brackets minus parentheses another. I need actually one more parenthesis here. 1 divided by D38 power 2 close brackets twice and then close brackets again for the third one. Hit enter. If it shows that hashtag shine, that means the cell may be not large enough. Yeah. So the best way is that actually reformat this whole cell, right click format cells and into scientific notation, 1 number and 2 decimal places. You can see that is very much different than the number one would expect, right? For the Rydberg constant. So the reason is actually the Bohr model is actually precisely valid only for hydrogen atom. There's a way to actually modify it for some other elements, but if the atomic weight is too high, it's not going to match anyway. So we'll just don't need to compare anything, just we'll observe that. Okay, this is going to be then 1 over meter, right? Unit. Okay, question. Let me copy paste that function to R of which u1. All right, any question? Okay, let's observe the other colors. There's three other colors actually possible, right? Let it run this one and then slowly observe the other colors. That a color? No, right? No? Oh, that's blue color again. We already have it. That's a purple. So the purple goes from 6 to 2, right? Purple color, and the wavelength is about like 405, right? So I can maybe edit this one actually. 405, which means 405, 4.05, and it goes from 0 to 2. And if I do that calculation for the purple color, I'm getting very reasonable answer actually. Close by, but it's still the error going to be a little bit higher. Okay, any question? Let's check other two. There should be two more colors, right? Let's continue this one. Let it run and then see what other colors are possible. I think there should be maybe at least one other color. We already done. If you do multi-atom system, then that will appear, colors will appear very quickly, but then we can't really see it. Oh, that is the other one. It's looked like green, right? Like light green. So that goes from last one is 4, is starting around like 6 or 7. That's difficult to see. If you observe the atom here, that will show you a started point, but I did not see that. Only way to see it now is actually maybe zoom in a little bit and then see where this green wave is starting. I think it's 6, right? Okay, let's try with 6 to 4. And the wavelength is about like 500, 10, 20, 30, 40, 45. 545, 545, e to the minus 7. And the green, actually light green, but that's okay. Goes from what, 6 to 4. Take it out, this number. Oh, too bad. Okay, question. Continue. I think there's one more color possible, right? Yellow, probably. Green we just did. You need to continuously observe until the different color appear. If different color appear, then you can pause the simulator and then read the information. Okay. Not yet. think two more colors should be visible. Let us see. That's the same purple color we already done. That's the other two colors. Green color we already done. Do a little bit more electron to see we can do it faster. Probably that way. Red we already done. Blue we already observed. Any other colors? I just increase the number of electron comes out from the electrode. You can do that by increasing the percentage of continuity there. It will speed up the process. Is that the only color we can see? Interesting. I saw earlier in when I put the multi-atom, I think we saw two more different colors, right? So that's what I try to observe. Let's wait and see a little bit whether we can get that. Did I record the red? No, right? Oh, that's why. Red also I did not record yet. If you observe the red, you can record that. Very difficult to see that. That's the yellow, actually. So, but I miss actually, it ended at 8, right? So, which means, oh, I think I missed that yellow color. Yellow and red both I have to record. Let's record at least one more color and then continue into the other. Okay, so it's gonna take seems to be lot of time because the usual colors it producing is the blue and the purple. Seems to be yellow is very rarely I can see. Blue is visible very easily. Blue is the most visible one. Because which means the transition you can see, this is the one we're gonna talk about actually, chapter number 8. These transitions are not happening from every single states, right? Because it doesn't allow to happen transition every single state. There are allowed transition and then there are not allowed transition. So that's where actually that's what we're going to talk on chapter number 8, how this how they actually make the periodic table. So we're starting from the hydrogen. When the electron filling up, it's not going to fill up like randomly everywhere. There's a particular rules it's following, right? Um, so that's what the focus of the chapter 8. Then you will see why it is not allowed some transition, why the some transitions are allowed, things like that. So I can't see actually yellow color at all. I don't know I'm going to see the red again either. Maybe you have to wait a little bit too. Anybody record the yellow? Anybody able to record the yellow information? Anybody able to get the information for red? That is for which color? 8 to 5 is the yellow? Okay, so I can use that actually. We just need that. Okay, so the yellow gonna be then we can read the I can read actually wavelength here because I have one dot here. That's good enough. 500 570, very close to 580, right? 580. Let's check. Equal sign 580 e to the power negative 9. 9 to 4. Okay, let's try with 9 to 4 then. Yellow. See what I'm getting. Okay. That actually two value is 2 of 9 to 4 is red. Then the yellow is 9 to 6. Okay, that actually very good number. Okay, so the red, let's take a look at that also. Red, I can read here 600, 680 equal 6. If you do equal and the number, it will automatically adjust into the scientific notation correctly. Okay, so that's why that equal sign is needed. You may need to add another cell if you want to do next color, because I have only 4 cells highlighted there in that table, but add another cell, it's not big deal, right? Another row there. Red goes from 9 to 4. Let's do that. That should be scientific notation. This should be, there should be 2 more zeros. Okay. All right. So the since we done earlier detailed calculation, we don't need to repeat it again and again, the same thing. So let's take a look the other possible spectrums. Okay. 9 to 4, actually, we got reasonable answer, but I did not see that actually both the yellow and red, you have to take a look again, okay? I'm not sure about numbers. I think the yellow also seems to be not even closer, 9 to 6. I just get the 2 numbers you guys provided. It seems to be taking a lot of time to observe that. Uh, that's okay, I think. With this part, we're just doing the observation. We're not doing comparing or any detailed calculation either. So I think it's fine. Just record it. I'm not going to reduce any points or anything. These numbers are off. But you can see this number is 2 off. Yellow 9 to 6. That number seems to be extremely off. I don't know. Maybe it's not 9 to 6 probably. Somebody told me it's 9 to 6, right? Be 8 to 5. Okay, let's try that then. Try 8 to 5. Yeah, that may be reasonable, I think. Yeah, but that's not meaningful. Okay, you have to really observe what you observe, record it. Okay, these two I will let you guys to try. So let's try the other spectrums because we can try two more, sodium and neon. Let's take a look. And before we do that, let me show you now where this apply because these are now not just anything abstract. Actually, we do in here, right? So the application you can easily see if you moving around the night in any city, you will see these boards. See that? These boards, right? If you go into any city, the different the shops has those boards. They light up on the night. So all those night lights is actually working with this gas discharge mechanism, really. Okay, except the LED ones now. That's a different scenario because these are all type ones. Okay. Nowadays, I think most of these boards are LED ones. That's completely different. But it's still that excitation and the de-excitation process is there. So that's the idea. That's where it's applicable. So this is hydrogen, mercury, sodium, neon. So let's try the other two. If you click on right here, it's a view picture actual discharge lamps. That will show up that picture. Okay. All right. So let's take a look. We done mercury. Let's do sodium. Let's go into the multi-atom here and then let's check how the sodium look like first. Sodium, check it out, how many colors it's making. Sodium seems to be making only two colors like the orange color and the yellow, right? That's only two colors. So let's observe that one. Those are just observation only. You can just make a new table out of here. This one, another table I'm making here. This is the table number 5, that for sodium. Okay, any question? All right, so let's take a look then sodium. Go back to the one atom system and continuous that the production rate you can keep it a little bit higher, then it's going to be a little bit faster. And sodium, let's try. That's extremely will be difficult to observe actually starting point you can see spectrum becomes very compressed. I don't know whether we can report it properly, identify it properly, but let's try. The problem with now, I already see the yellow from 2 to 1. That is easy. Okay, so let's put here yellow. Wavelength is about 590. 590, it goes from 2 to 1. You can see it's completely different. So which means when you go into a more than above the hydrogen, that formula works very nicely, right? Anything beyond hydrogen, the formula doesn't work. There is a way to actually modify that by using the atomic number, but that also working only very limited area. If it is the weight of the element is really heavy, so that cannot explain at all. So there's one more color we can hopefully detect, I think. Did I done the yellow correctly? It's all right. Okay. So let's check the other ones. There's only two color we detected earlier, right? Orange and yellow. It appears they are 6 to 3, I think, but I did not see it clearly. I want to check that again. 2 to 1 is yellow always, but I think when it goes to 6 to 3, it produces that orange color. Observe carefully. 6 to 3 or maybe 5 to 3. 2 to 1 is fine, the yellow. Everything else either very low energy IR region. I think it's 6 to 3 is the orange color. Yep. So it actually 6 to 2, right? Yep. So if you go 6 to 2, you can actually get the orange color. That is about 610, close to 620. You can read into 615 or 20, doesn't matter, I think. 20 or 16. So let's read into 615. 6 to 2, you can see the numbers are way off. Let me take a look. All right, any question? Okay, so let's observe the same behavior for the other possible spectrum which we can do is, I think, the neon. If you want to see the colors of that, you can click on this picture. That's the neon. This is actually in real life scenario. If you have a gas discharge light, if you observe that through diffraction, then you will see the diffraction pattern. Okay. And let's see by using the multi-atom tube what the number of colors it can produce. That way it's easy to recognize what we are looking into first, right? Okay, that actually can make various type of red colors technically, right? You can see range of red colors. It has very light red colors all the way to orange, and then very dark red and yellow and the light green. Everything else seems to be making UV. So the different like various red colors, I don't know anything meaningful. Try to record it, but let's record at least 3 different colors, maybe green, yellow, and orange at least. Okay, or one of the red, at least 3 of them by using single atom system. Okay, any question? That also I'm gonna make a table by using the same table, or I can actually extend this table for the other next spectrum. Instead, maybe I should make another table. That's better, I think. Let's do that. You just need to copy paste this table as it is. Okay. If you copy the whole table, it will even copy with all the calculation and everything. That much easier. You don't need to redo the calculation or anything. It's the same thing. All we need to do is actually edit this part. Now I'm recording atomic spectrum for neon. And then these numbers will edit accordingly. Okay, so I can record, I think, at least maybe 4 different colors. 4 different colors. You may need to edit a little bit this table. Formatting, I mean, not big deal, I think, right? So let's erase this one. So let's observe the first color here, which we don't know which will show up first. But if you edit this, the calculation will done automatically, right? So now I add actually 2 new tables. Okay, the table given had only 4, but this 5 and 6 I add later. Okay, format accordingly because your report should contain all of them. And this is an easy report, I think, in terms of theory and everything, nothing much to write it down. So I would suggest do this report too. Then by next week, you actually completed 10 labs. If you complete all 10 labs, we'll talk about Monday. And if everybody happy with the 10 lab grades, then we don't need to do the 11th lab. We can even skip that. But If anybody need it, I gonna do it. Okay. If not, we will skip that. Instead, Wednesday we can continue the lecture class. All right. So let's do the last observation. Then actually we done. All right. Any question? Okay. So let's check it out. This one then. Neon spectrum. Now the problem is, I don't know whether we can read the energy levels, right? You can read actually from the atom. That's the best way to do. And also you need very high energy really. If the energy is here, you're not going to see anything. You need really, really high energy. Can I produce higher energy? Probably. Oh yeah, this one with the single atom system, actually you can't do the observation. You can see energy of the incoming electron is actually on this level. You can't really do that at all, the observation. It's impossible to do it here. But multi-atom is actually showing us. Only problem is that identify the states, because with too many atoms there, I don't know whether we can identify, right? Let's run in slow-mo mode to see whether we can see it. Maybe we can identify because that photon going out actually has the color. If I recognize exact point where the photon goes out, that way I can record it. But seems to be it impossible to record that, right? By using the multi-atom system. Maybe we have to skip that. Neon spectrum seems to be not much meaningful, because the single atom system doesn't allow us to see anything. You can see the maximum energy we can get here, but there's no any states in between. You have to have the state in between than the maximum energy you can get. Then only you can see that. But if I do multi-atom, then I can do it. But I can't actually see, I can't distinguish out which one producing which color. It seems to be very impossible to do. I think we should skip that, probably. Not much meaningful. Okay, any question? Anybody have any question? Because you can see numbers from after 1, 2, 3, 5 very close by, then the 6, 7, 8, 9, 10, all of them are extremely close by. There's no meaning actually. Try to read it at all. So we should skip that, probably. Okay, I think that's enough. It's not really anything new either. It's going to be the same. I think we should stop from table number 5. You can get rid of table 6. No need that. Anybody have any question, concern? Okay, no problems. All right, then let's take a look very quickly. Some of the stuff we can discuss from last chapter, and then we have like half an hour. So let's discuss one question from last chapter. Okay, anyone has any problems with this lab? Any concern? Anybody still working on calculation on any of the previous tables? Okay, then let me open up a new window.